All right, so I'm happy to be here. Thanks. When I was invited, I looked at the list of all the other speakers, and I noticed there was a lot of Bayesians on the list. And so I thought I better give a frequentist counterpart. If there had been a lot of frequentists on the list, I would have given a Bayesian counterpart. I'm just sort of a contrarian at heart. So that's not entirely the goal of the talk. So the goal of the talk is to sort of, it's a summer school to teach a little bit about Bayesian frequentist distinction, emphasizing a little more the frequentists, because I think you've probably had more Bayesian during the week, and emphasizing the essential unity of these two classes of ideas that have been debated for about 400 years now. So I'm not going to really ask this question, but let me, I am going to ask the question. So let me, you've been through 2 weeks of mainly Bayesian lectures. How many of you think that you're a Bayesian? Would you call yourself a Bayesian? All right. I'd say about a third of the room. How many of you are a frequentist? All right. About 3 of you. See, so that's kind of weird. How many of you are both? Another third of the room. How many of you are neither? All right, so I'll ask that same question maybe at the end of the lectures and see if things have shifted at all. Okay, so this topic that most of us are interested in, statistical inference, has been around for quite a long time. And there are 2 sort of main perspectives that have stood the test of time, the Bayesian frequentists. I'm going to give you a little argument in a couple of slides from a decision-theoretic point of view of why these are really the only 2 real competitors. Essentially become because loss functions have 2 arguments, so there's kind of only 2 ways to go. It's really important to kind of keep, throughout your whole career, balancing these 2 things back and forth. Anybody who decided they're one or the other early in their life and they were only that, I think, is sort of missing the point. These are kind of things to ponder and muse and understand the relationships. And they're deep. So Bayesian perspective is a conditional perspective. So inferences should be made conditional on the current data. So you just observe some data, hold that fixed, and do everything conditional on that. Don't worry about other data you could have gotten. That's the conditional Bayesian perspective. Now, I find myself often being a Bayesian in applied projects when I'm working with a domain expert and we have a lot of time to work with each other. So in particular, like lots of biology projects, you'll have someone who knows a great deal, and you want to try to understand what they're thinking about the problem. What do they know? What's the prior? Also, what is the loss function? So we often concentrate on the priors, but you really also need to concentrate on the loss function as well. So what do they care about? So if you have time to elicit all those sorts of things, it's often really very appropriate to be a Bayesian. And one way to think about what a Bayesian perspective is, it's the optimist. So I'm approaching a problem as a statistician. I want to get knowledge out. I want to get inference out from data. So we have the sophisticated tools. Let's be optimistic and assume we can get as much knowledge out as possible by working hard to get a good prior and get a good loss function and get a good model and iterating. So that's the optimist. The frequentist perspective is an unconditional perspective. You don't think about conditioning necessarily on the current data, all you could, but the way you evaluate a frequentist procedure or you evaluate a procedure from a frequentist point of view is that you consider unconditional averages. So you should get good answers in repeated use. So repeated use means you're going to look at multiple data sets and you're going to take averages unconditionally over the multiple data sets. You don't condition on one single data set. You look at multiple data sets you should get, and you talk about unconditional performance over all those possible data sets. That's what it means to be a frequentist. Now, I also think this is a very natural perspective for lots of situations, and I often find myself being a frequentist. In particular, if I don't have a lot of time to sit down with a domain expert, and we just have a very quick sort of project. I'm going to maybe develop a very simple tool that aims at some inference directly in some sense and hope that I can prove something about it or someone else has already proved something about it, that I'm not going to go wrong by using this. So in particular, if you're going to write a piece of software that's going to be used by many people with many data sets, you really ought to give a frequentist guarantee on that. You ought to be able to say that piece of software is going to work well on multiple data sets. Now, inside the software, it may be Bayesian. It may condition, all right, but you want to be able to say whatever you condition on, multiple different data sets, you should do well. Okay, now someone sort of worked all that out in advance in some sense. That there are some theorems that say that Bayesian inference has good frequentist properties under various situations. So in some sense, you don't have to worry about it that much in kind of classical situations, parametric situations, and so on. Non-parametric is a different story. But in general, if you're not going to necessarily start with a conditional Bayesian procedure, you like some other procedure. I'm going to compute the median or something. Didn't necessarily have a Bayesian justification, but I like it. It's a procedure. Then that's my software. I want to prove that it has good frequentist properties, meaning that a large fraction of the time it'll give the answer you expect to get on all kinds of data sets. Okay, so I find that a hard argument to find difficulties with. I mean, it really, if you're writing software, you should be a frequentist. Now, the frequentist perspective also is that of a pessimist. So instead of being an optimist, what we think about it, if you're a frequentist, is that we're going to write down a model, we're going to develop a procedure, and almost certainly it's going to be a simplification of reality. Okay? Reality is really complicated. We're going to simplify it drastically often. And so we may get the wrong answer. And let's protect ourselves not to get the wrong answer too often. Okay? So in medical domains, a lot of people tend to be frequentists because they want to protect themselves about doing something wrong, something stupid. Okay? So it's the pessimist perspective. So frequentism has definitely dominated statistics in the last 100 years. The Bayesian world is certainly present, but it's smaller. And I think most statisticians were trained as frequentists and still tend to approach the problem from a frequentist point of view. And it's just this sort of pessimism, just sort of ground in. And there's lots of good reasons for that. There are lots of situations where people have made bad inferences, and the pessimistic spirit is an important one to ingest. Okay, now I'm often asked, I go back and forth between the quote-unquote machine world and the learning world and the statistics world by statisticians, what is this thing called machine learning? And I don't really believe it's a new field per se. I believe it's a contribution to the general problem of statistical inference and decision making. And it really is a set of themes. It's not one kind of a field, but it's a loose confederation of themes. So reinforcement learning, clustering, classification, graphical models, I mean, what do they have to do with each other? Not directly that much. They just happen to be themes that people have found interesting and useful. And they connect to each other, usually by some sort of a statistical argument of some kind. Statisticians I talk to are often a bit relieved. Oh, it is not. They don't actually pretend to think they've discovered a new field. It really is just sort of statistical inference. Okay, at least that's good. But it's a sort of different flavor in some ways, and one of them is there's a lot of focus on prediction. If you just can make a good prediction, I don't care how you did it. That's often the machine learning spirit. And on kind of completely other side of things, don't worry about prediction, but just do exploratory data analysis. Find cool features. This is a kind of a typical machine learning thing to do. That's exploratory data analysis. You're trying to somehow understand something about your data. And so statisticians, nod their head. Those are both things they understand. That's reasonable. That's part of statistics too. But a lot of statistics is about what's called coverage. I want you to tell me something about your confidence in some prediction you have. Okay? And I want you to tell me you found some structure, you've done some exploratory analysis, you found some structure. What's actually the probability that's real, or what's the probability that that's garbage? And so that kind of goes on the terminology of coverage. I want you to, it's a frequentist concept typically, to guarantee me that if you run your procedure over and again, you will kind of do the right thing, i.e. cover your error bars will cover the truth the right fraction of time, or the things you will have discovered will be noise the right fraction of time. So statisticians kind of, not say, well, okay, they still haven't kind of matured enough yet to really understand that this is an important issue, to worry about error bars in a frequent sense, coverage, notion of coverage. The other thing that you'll note from machine learning people is there's a lot of focus on methodology. So everybody develops a new model, then a new method to fit their model. That's the focus of things. Not so much about kind of classical inferential topics. And then the evaluation is usually not theoretical, but empirical. So that's kind of good, and statisticians, I think, appreciate that. And then there's a kind of a dollop of empirical process theory. It's often called statistical learning theory, but it's really empirical process theory. And it's when they turn to theory, they turn to this big hammer. And they don't kind of use all the other little hammers that are sitting around that are available, mainly asymptotics. So there's lots of non-parametric statistics in machine learning. In fact, very few people do parametrics. But surprisingly to a statistician, there's hardly any asymptotics. That's the main tool to a statistician, is all these asymptotics. And everyone's using these big empirical process type hammers. So that's a bit of a surprise. And the other somewhat surprising fact is that the field is sometimes frequentist and sometimes Bayesian, and it's not clear when one's going to come up and when the other's going to come up. And it kind of is a coexistence. You have a lot of people doing just purely Bayesian stuff, and a lot of people doing frequentist stuff, sometimes not even calling themselves frequentist. And there's no interplay between those two things. So there's just kind of two parallel streams that go forward. And occasionally you'll say something, well, I can give it a Bayesian interpretation of your procedure. Here's a prior that matches it or something. But very little actual kind of real interplay in the usual statistical sense. Okay, so you guys are more machine learning people, so this slide may have not meant that much to you, but I think it is important to understand how you're understood by the outside world. Okay, so I promised a decision-theoretic perspective. Decision theory goes back to Wald and to others in the 40s. And although sort of the number of papers that have decision-theoretic content to them has dropped over the years, it was the thing to do in the 50s and 60s. It's still definitely present, and I think many people, including myself, view it as an extremely useful perspective to bring to bear in thinking about fundamentals in statistical inference. Decision-theoretic perspective says you have some data X. Let's consider a family of probability models indexed by a parameter theta. And I put parameter in quotes because it doesn't mean a finite dimensional parameter. It just means an index of a class of probability distributions. If that class is infinite, as it often is, like a function space, then theta indexes all the functions in your function space. Okay, uncountably number of things. So people often pick up a decision theory book and they see theta there and they say, oh, this is just parametric stuff. This isn't relevant to me. And that's completely wrong. Okay, completely wrong. So theta indexes a function class or a measure space, anything that you want. Okay, so that's our family of probability models with an index. And now having gotten data, we're going to define a procedure of some kind, maybe a decision tree, maybe a support vector machine, maybe a graphical model that will take that data and produce some sort of a decision, an estimate, a function, a decision of some sort. All right, and now given that decision and given the underlying probability distribution that generated, indexed by theta, you define a loss function. Okay, how bad you're going to feel if the truth was one thing and you made a decision of the form delta x. Okay, and I think almost any statistician would be happy at this point. This is all fine. This is what you want to do. You need to write down a loss function, okay, to evaluate how good a procedure is doing. And now we're going to have multiple procedures. It could be a delta 1, which is your decision tree, and a delta 2, which is my support vector machine, and so on. And I'd like to compare these, say which is best, either in this situation or in many situations, hopefully. So how can I do that? Well, the loss function should somehow tell me. It's my measure of how good I'm doing. All right, but the problem is the loss function isn't just a number. I want to get a number to compare two things. That procedure has loss 3.5, and that one has loss 4.2. That one's better. But it's not just a number because there's two unknowns there. X is random, so there's kind of an unknownness about X. And theta is unknown. I don't know the probability distribution underlying the data. So I got two pieces of things that are unknown. How can I actually optimize over loss functions, choose the right delta? Okay, so that's kind of the core problem that the decision tree aims to face. All right, well, you got two arguments of that function, so there's going to be two perspectives on how to get rid of that unknownness. You start with the delta x or you start with the theta. And those two perspectives are called Frequentist and Bayesian. Okay, and that's my argument as to why there are two of them, because there's only two arguments to loss functions. Okay. All right, so let's talk about the frequentist one first. So the frequentist looks at the loss function and says, well, you got two unknowns there. Let's start with the x one, try to do something about turning that random x into a number somehow. Well, if it's random and we want to turn it into a number, we need to take its expectation. So let's take an expectation of this quantity. Let's take an expectation of the x part. Okay. Well, an expectation with respect to what probability distribution? Well, let's use the same theta to take our expectation as is in the loss function. Okay, so I don't need to know the truth a priori. I just say whatever the truth is, I will take the expectation for that, and I'll do this for all theta. So I'll look at all possible truths. And so I'm going to get a risk function. The frequentist risk here is a function of theta. I haven't picked which theta a priori is the truth. Okay, but this quantity here, this E sub theta, is the expectation under the distribution indexed by theta, and it's an expectation over x. So the x goes away here, and we just get theta on the left-hand side. All right, and that's a key. So if you need a definition of frequentist, this is probably as good as any. In fact, this is kind of one message I want to give to machine learning people. A lot of people in machine learning are frequentist. A lot of the work is at least frequentist. But you never see the word frequentist, and you never see people talking about the definition of what it means to be frequentist. All right, well, here it is. Here's one. It means you take an expectation for fixed theta with respect to x. And in doing that, what you're being not Bayesian at that point. You are taking an expectation with respect to other x's or over the entire sample space. Not the x that you saw, but other x's you might see. Okay, so that's what it means to be frequentist. You're looking at other possible data you could have gotten. It's the unconditional perspective, and it's exactly that. So whenever you write down an E in an equation, and it's an E, averaging over X, you've just veered away from the Bayesian route and you've gone towards the frequentist route. Hope that's clear. Okay, so that's what the frequentist does to get started. And now they have this function R of theta, and they say, well, I don't know what the truth is. It could be any theta, and now I need to still convert this thing to a single number. How do I convert that to a single number? Okay, and now there's many possibilities, and there's been huge literature, 50 years of kind of work on ways to think about turning this into a single number. So the one that you probably heard the most about is minimax, where you'll take the maximum of this frequentist risk over all theta, and then find the procedure that has the minimum of the maximum risk. Okay, and a lot of good work has come out of the minimax perspective. That's one way to get rid of the theta part by taking the maximum over all theta and then taking the minimum over that. So that's minimax. But there are other ways to do this. You could take subclasses of procedures. So delta x could be in a subclass, maybe all unbiased estimators or some other invariant estimators, so on. And in that subclass, this R of theta might actually have a simple characterization. You can actually get out a single number over some subclass. And there are many other kind of ways of trying to approach that. Another thing you could try to do here would be to average over theta. All right? But when you average over theta, you've got to average over some distribution on theta. And at that point, you become Bayesian. Okay? You're trying to say something about a distribution on theta. So the frequentists are willing to do that in mathematics because you can get out some interesting mathematical results, but in practice, they're trying to avoid doing that. The Bayesian, on the other hand, welcomes the opportunity to integrate over theta because they think it's fine to put a distribution on theta. And they're going to do that, and since they have one sitting around, they might as well average this quantity now not with respect to x, but with respect to theta. And so here, this E over here is a different one. This E is a conditional expectation given the data x, it's a conditional perspective, an expectation over the theta part of the loss function. Okay, so this is still now a function of x, all right, but that's less troublesome now because the x is assumed to be conditioned on. It's known, it's fixed. So this is now a single number, and that's called the Bayesian risk. So we have the frequentist risk and the Bayesian risk. Okay? Bayesian should be interested in this because having defined this now, they can optimize over delta. And they can find the right procedure. Should I report the conditional mean, the posterior mean, or the conditional median, or so on and so forth? Well, that depends on which loss function you have here. And by optimizing over delta, you can pick that out. So if you haven't picked out a loss function, then you just report the whole posterior. But if you have a loss, then optimizing this equation will tell you which procedure to use. All right? So you don't see enough of that kind of work in machine learning literature of choosing the loss and talking about this particular risk function. And then this one you see a lot because this is what statistical learning people work with, and all other frequentists, this frequentist risk. Okay, so the frequentist goes to the left, the Bayesian goes to the right, and now you can sort of ask what happens if I keep going. So I can take this quantity here, and I can act like a Bayesian and average over theta. I can take this quantity here, and I can act like a frequentist and average over x. And neither camp would be very happy with you, all right? But what would happen at that point? Well, you get a single number because now both things have been averaged over. And will that number differ on this branch and this branch? Yeah?
Here's a small point. I'm just curious about the difference in your notation for expectations. On the right-hand side, you've written as conditioned on x. On the left-hand side, you have a such bit.
Yeah, this is just the conditional expectation of this random quantity. It's random with respect to theta. It's conditioned. This is a constant. It's just a random quantity with respect to theta. So this is the expectation with respect to theta conditioned on x. Or over here, this is the usual frequentist notation. They don't want to treat theta as a random variable, so you put it as an index. So this is just the expectation of that particular probability distribution. It's not a conditional expectation. It's unconditional. Anyway, do you get the same number by doing the two calculations? Yeah, what's the theorem that tells you get the same number? It's called Fubini's theorem. Okay? It's just iterated expectations. You can switch the two expectations. Okay, and what number do you get when you do those two expectations? It's called the Bayes risk. So you may have heard of the Bayes risk out there, and you might think you have to be Bayesian to use the Bayes risk, and that's wrong. That's not right. Okay, the Bayes risk is gotten by either path, the frequentist or the Bayesian path. Okay, so that's a little bit of decision theory. Hope that was interesting. Let's talk about the issue of coherence and calibration. To me, this is a very helpful way to understand some other relationships between Bayesian and frequentist ideas. Let me just actually, before I do that, I said the word relationship. So if you go back to the previous slide, decision theory has been really the home of a lot of relationships between Bayesian and frequentist ideas. So in particular, if you try to find optimal frequentist procedures and define them in various ways, there's something called complete class theorems that tell you that they are either Bayesian procedures or limits of Bayesian procedures. So from a frequentist point of view, you often want to use Bayesian procedures because you know that they give you the class of optimal procedures. And of course, the frequentist doesn't necessarily use that theorem in practice because you don't know with respect to what prior, you're completely unknown what prior, but you know mathematically that's a fact. So that's one class of connections between Bayesian and frequentist. Okay, so coherence and calibration, these two words are used a lot to describe kind of bias, perspectives on inference. David Draper has written a lot about these particular words and a lot of other people as well. So there are two important goals for statistical inference. Coherence, means coherence, that you give out the same answer kind of no matter what question, I give out the same answer no matter what question you ask me, and you can't find any incoherence among my multiple answers, something like that. And calibration is, means something like if I give you a number out, then that number means something. That if you ask me to do a procedure multiple times, and I claim that 95% of the time I'm giving out the right answer, well then 95% of the time you better give me out the right answer. That's calibration. Okay, so Bayesian work has focused on coherence, while frequentist work hasn't been too worried about coherence. I think that's probably a fair statement. So Bayesians get kind of coherence for free because they have a joint probability distribution underlying everything, and that's the source of the coherence. And then they love to bash frequentists because they find places where frequentist work is not coherent, and lots of papers written about that. And the frequentists are not so worried about that. They are interested in a particular inference problem at one particular time and doing the best, finding a loss function that targets that problem. And you can't be coherent all the time. That's just life. Somehow it's kind of, one might shrug one's shoulders. I'm certainly not coherent. Well, coherent is maybe the wrong word. I'm not coherent in the mornings. But consistent is perhaps another word, but that has another technical meaning. So I'm not consistent either. I'll tell you one thing one day, and then I'll tell you something else 6 months later, and that's just life. Now, on the other hand, frequentist work has tended to focus on calibration. So calibration, again, kind of is like this notion of coverage, that the numeric values you associate with your procedure really do come out in practice. And Bayesians haven't been too worried about calibration. Okay, now that's kind of a bit of a problem with the Bayesian perspective. You start writing out a bunch of priors, you write out a procedure, you run it on your data, and that's it, you're done. All right, what guarantees did you give me, and could you tell me, that you did that procedure multiple times, it would come out to have your guarantees turn out to be true? All right, well, Bayesians don't tend to worry about that, that much, enough. Now, good Bayesians, most Bayesians in statistics are actually a little bit frequentist too, and so they will often look at a little bit of a frequentist analysis of what they're doing and compare the coverage, for example, of their Bayesian procedure. Anyway, if you don't do that, if you're a pure Bayesian, then you certainly get coherence, but you don't necessarily get calibration. Now, on the other hand, if you're a pure frequentist and you're worried about pure calibration, you can be calibrated and completely useless. 95% of the time you give out error bars that are a point, and then 5% of the time you get error bars that cover everything. And so that the average works out to be some kind of confidence interval, but on any given set of data, you give out a useless answer. So you can be completely loose if you're purely calibrated. On the other hand, if you're completely coherent, you can be completely coherent and completely wrong. It's completely coherent to give out the answer 1 to whatever problem you ask me. Okay, Okay, and so most statisticians find some kind of a blend a natural way to proceed because they tend to achieve both coherence and calibration. So I've in some sense given you the answer of my question in my title. I think many statisticians, not every single one, but many of them find that they are both a little bit Bayesian and a little bit frequentist. And these things can be made into conflict. There are ways of focusing on calibration and coherence and showing that one perspective doesn't achieve it. But they really do act complementary and aid each other. And it's a little bit like wave-particle duality. It's one way to think about it. Sort of waves and particles are both there. They're both going to always be true. There's something right about both of them, but they don't quite really work out, together as well as they should. I think it's true about Bayesian frequentists too. They're both right in some way. They're both around forever, and one's not going to vanish. But they don't quite, merge entirely. They do fight each other in various ways, in particular in testing and model selection problems. And I think there'll probably eventually be some more of a resolution there even, but it's going to take a while. All right, so a few more comments about the kind of the sociology, really. So the frequentist world is this hodgepodge of people, can do any kind of technique as long as you give me an analysis. That's frequentism. So it's just a big, big field. Bayesian is a little smaller, and it's really got two main subdivisions. So you have subjective Bayes and you have objective Bayes. This is simplifying, but these are the kind of the two main schools of Bayesian. And the subjective Bayesian is, believes that the prior comes from a person, or maybe a small group of people. And so the goal is to work with that person, a domain expert, and you want to figure out what's the prior that person has in their head. And what loss function do they have in their head also? And then the model, too, is somehow had to come from the domain expert, so you've got to also figure out what the model is, elicit the model. Okay? And the subjective Bayesian argument is that if you got out bad answers from your Bayesian procedure, it's just you didn't work hard enough to get the prior and the loss function in the model. You should have worked harder. All right? And put that way, it's sort of hard to argue with. If I spent 1 million years and got out the right prior, I would get out the right inference. So what kind of, once you have the prior, the loss, and the model, you're done. You use Bayes' rule and so on. There's not much else to talk about. So what kind of research do you do as a subjective Bayesian? Well, you do a lot of things you saw here this last 2 weeks. I think a lot of the work you probably saw was, effectively, subjective Bayesian, even though I'm not sure those words were not used. What does it mean? Well, you develop new kinds of models. All right? Why? Well, because I'm a subjective Bayesian. I'll go out and face some new problem. I'd like to have a library of models I might bring to bear on that new problem. Okay? So if a lot of people have worked on models, I'll have a big library. So that's one thing you can do. The other thing you can do is that Bayesian, Bayes' rule, you have to integrate. You've got to get that denominator. So you better develop lots of procedures for integration, because that's going to be hard to do. So a lot of algorithmic work goes into subjective Bayesian research on integration. And then a thing you probably didn't talk as much about, but if you're going to be a real subjective Bayesian, you really ought to worry about how to get those priors. It's not that easy. And you better work out techniques for eliciting and assessing priors from individuals. And there's a whole literature on that, and a lot of Bayesian neural network, machine learning people don't focus on that nearly enough. So if you really are going to be a Bayesian, you better worry about how to do that. Anyway, those are the kind of some of the main areas of research. There are others, but those are the main. So there's not a lot of focus on analysis of did my procedure work and so on. That's really what frequentists do, because if you have the right inputs, the Bayesian output's going to be a good one. All right, so again, you can't really argue about that from a philosophical point of view. It's coherent, it's pretty, it's nice. But in practice, there are really lots and lots of problems. And the main one is that lots of us work with really complicated models. There are hierarchies, there's multivariate quantities, there's matrices, so on and so forth. And all of those bring new parameters into the problem. Whenever you wrote down a Wishart distribution, you got a whole matrix of parameters sitting there. All right, you got to put a distribution on that. All right, well, okay, that's hard. And so the more complicated your model gets, the more parameters, and it's now going to take a long, long time to get a domain expert to kind of say, well, my prior on that Wishart thing is this. And moreover, if you've got long list of parameters, it's really the joint distribution of all the parameters you better be assessing. That's what you're supposed to get. Right? That becomes really hopeless. How do you do that? Well, then you start making independence assumptions. You start throwing them in, because if I say, well, that's independent of that, now I can think separately about this and think separately about this, then the human domain expert can get in and start thinking about it. Now you're leaving Bayes on the floor a little bit, because you're not really assessing the right prior. Simply, for computational reasons, you often start writing down lists of independence assumptions. And at that point, you may have left kind of optimality behind. And now a subtle issue, but just as important as the others, is that it's really hard to get domain experts to assess tail behavior. And whenever you're working with real valued quantities, which of course most of our models are, as you go high enough in the hierarchy, they start to become real numbers. You want the probability of some discrete thing. Well, the probability is a real number. You've got to put a prior on that. So it has tail behavior you have to worry about. What tail behavior? Well, I could get my mother to tell me about the mean and the standard deviation of something, but she can't tell me about whether it's Laplace tails or t-tails or whatever, right? And I don't think many of you could either. I don't think I could. It's really hard to assess those things. And it's also hard to kind of learn them, quote unquote. Hard to get ideas of tail behavior. Does that matter? Well, in some Bayesian models, it doesn't matter that much. But in lots of Bayesian models, it really does matter a lot. In fact, in some cases, it determines the entire output of your procedure. And this is a really serious issue. So you will often hear people talking about Bayes factors and marginal likelihoods. How do you solve model selection problems as a Bayesian? Marginal likelihood. It's the knee-jerk answer. Calculate that. All right, well, the marginal likelihood is the integral of the likelihood under the prior. It's not the integral under a posterior, which tends to sharpen up, and tail behavior doesn't matter. It's under the prior. So the tails are there. And your integral is, if you have very fat tails, it's going to be largely determined by your tails. That's in the prior. That's your assumption. Okay? And so the marginal likelihood can be, hugely determined, affected by your particular assumptions. Bayes factors, similarly, Bayes factors are ratios of marginal likelihoods. And so one way you might try to go is say, well, use improper priors. Try to make them flat, so I'm not putting very many assumptions in. Right? But as I think you may know, marginal likelihoods, if you're integrating under the prior and you have an improper prior, it has an arbitrary constant. And those things will tend to divide out when you calculate things like posteriors, but in marginal likelihoods and Bayes factors, they don't. You have a ratio of arbitrary constants. And so the Bayes factor is meaningless in that case. Right? So these are really serious issues, and there's a lot of statistical literature on this. There's things like intrinsic Bayes factors and fractional Bayes factors and various kind of ways to approach this. But if you don't try to at least think about those things, it is not the solution. It's not the hammer that solves the model selection problem. Okay, so tail behavior is a big issue. Non-parametrics. A lot of us, in fact, when I wear a Bayesian hat as a researcher, I'm very interested in non-parametrics and have been for about a decade. I think it's great. It's awkward for subjective Bayes because it's really complicated. A non-parametric Bayes model is hard to think about. It's these stick-breaking things and infinite objects and so on. What's my subjective prior on those things? And so a lot of subjective Bayesians, in fact, are not very happy with the non-parametric Bayes movement. Okay. So that may eventually get worked out, but it is currently an issue. Okay, so that's kind of some of the problems that arise, and I belabor them perhaps a little bit because I really think there's a tendency to just sort of say that the Bayesian perspective is so easy and systematic, how could anyone do anything else? Well, these are real issues that come up in real life. And then the last one is more philosophical, which is just that a lot of frequentists don't like sort of subjective Bayesians sort of telling them they can't use a certain method. So I like the support vector machine because it works. Right? I go in lots of applied situations. I will roll it out, and it will work really well and solve and everyone's happy. I get paid, and the company, makes money. What's wrong with that? All right? Well, it doesn't have a Bayesian interpretation. At least an obvious one. You might really be able to work really hard and find one, but it doesn't have one. It doesn't seem right. Well, do I have to wait around for someone to show me it's Bayesian to use it? No, I could just use it because I can write it down. It works, and then I can actually do some theory that shows that it has a frequentist, justification. All right, and there's lots of some simple kind of non-parametric testing situations where I just got a column of numbers here and a column here. I want to say well, those two columns are different, right? Well, there's these simple things that you just sort them and you find is column 1 more higher in the list than column 2. Develop a statistic that measures that and then prove that will work on repeated usages. It's a perfectly good kind of approach to testing. I'm not supposed to use that because that's not Bayesian. That just sort of doesn't feel right. Okay, so I hope I bashed subjective Bayes enough that you'll be interested in some other things. Yeah?
Sorry, going back to tail behavior and Bayes factors.
Yeah.
So you were saying that, if it was only the posterior that you had to integrate over, then it would be better because that would sharpen up and maybe it wouldn't matter. But you're integrating the likelihood, and the likelihood does sharpen up. So it doesn't matter whether it's the integral of the product of two things.
Yeah, no, it does sharpen up. No, it does sharpen up, but it doesn't. It's the rate at which things sharpen up, and you've got to pick your tail behavior to have a certain rate to compete with that, and then you've got to do that effectively in your two models, in the numerator and the denominator, and it's sort of getting all those right rates to line up which is hard. Yeah, I sort of maybe a little exaggerated. The likelihood does sharpen up. You're right, but it's important. A lot of people sort of think, well, problems go away when you integrate against a posterior, which is true, but the whole point of marginal likelihood is you're integrating against a prior, so the tail behavior still has to be taken into account. Okay, so objective Bayes. I really like objective Bayes. There's a whole conference on this that I went to the last couple of years, and I think it's like OB09. If you'll type that in, you'll see the objective Bayes conference. And so this is a great perspective. It really is a bridge between frequentist and Bayesian ideas. It's trying to find ways to set priors that aren't subjective. Maybe no human would have come up with them, but in some sense they're sensible. They would they will protect you from making bad inferences. And moreover, in really complicated models, it would maybe give you a way to set priors automatically that you don't have to have a human go looking at the long list of parameters you have. All right, so there's been a lot of work on this. Probably the best existing class of techniques are called reference priors. It's a whole talk on its own. But what they do is they set up a variational problem where they maximize some notion of divergence between the prior and the posterior with respect to the prior. Okay, so the distance between the prior and the posterior in some sense is the likelihood. So if you maximize that distance, you're making the likelihood do most of the work and the prior do as little work as possible. So that's a well-posed variational problem, and you can solve it in many situations, and you get out a prior. So this prior hasn't been gotten from a domain expert. It's gotten from a piece of mathematics that tries to protect you about having an over-influential prior. In many situations, you get out improper priors by doing this procedure, Jeffreys priors and so on, but in not all situations. You get out proper priors in some situations as well. So anyway, this is an ongoing research project. It's very interesting. I would have hoped there would have been lectures about reference priors here, but probably there were. And so objective Bayesians, how did you pick the reference priors was a good idea? Well, it sounds like a good idea, but how did you actually kind of show it was a good idea? And moreover, there's many other kind of approaches to priors. How do you choose between procedures or principles for choosing priors? We're not being subjective. So you use frequentist ideas. You will often sort of show that your Bayesian procedure, choosing priors in some way, has good frequentist properties. And people kind of agree that's not a bad way to kind of get a guidance. Consistency properties are sometimes used. Admissibility properties are widely used. That's another frequentist idea that are to try to get good principles for choosing priors. Okay, so I like this framework. It's a great area to work in. But kind of the downside is it can be challenging to work with in complex models. Okay, so you have to kind of do the mathematics to get out your prior, and often that's really hard to do. And so it's an ongoing research project to kind of do that. And I'd say for simple models, this is often worked out, and this is an off-the-shelf solution. But for a lot of the models that many of you will be interested in, it's not off the shelf. So you have to do a lot of work to use objective-based ideas. All right, but I just want you to be aware that this is a counterpart to subjective Bayes. Okay, so lastly, the frequentist perspective. So the frequentist perspective is very Catholic. Procedures can come from anywhere. They don't have to be derived from a probability model at all. They don't have to be conditional, nor they have to be derived from a probability model. So non-parametric testing, just kind of sensible sets of test statistics and show that they work. Support vector machine boosting are kind of things that weren't derived from a probability model. Also, I'd like to mention things like methods based on first-order logic. All right, so you can have a data set. Data comes in. You have a big first-order logic machine, and out comes some answer. All right, and that's good. Nothing wrong with that. And as a frequentist, I would want to sit down and say, well, is that a good procedure? Is that just because it's logic doesn't mean it's necessarily good, but it might be good. But I can analyze it from a statistical point of view. And that's what frequentism does. It would say, okay, does that procedure on repeated data sets give me an answer which is good in some notion of a loss? Right? And so I often get in an argument with people in kind of the more AI side of machine learning saying, well, there's statistical machine learning and there's the rest of machine learning. And I would say, what is that other object? What's the other part of machine? What logical sort of stuff? And I say, well, these are completely agreeable perspectives. You can take your logical thing and I can evaluate it statistically. And they say, well, okay, that's fine, but Bayesian, that's different from logical. And I just sort of start finding these distinctions a little bit unhelpful at times. So this frequentist perspective in particular is just an analysis tool, and it can analyze all kinds of things. So I think of machine learning as statistical, is the inferential problem of taking in data and getting out knowledge. Right? And frequentist perspective is very much part of that. Okay, so if you can get your methods from anywhere, I can write down, Mike Jordan's silliest method ever, and you want to be able to rule that out. So what frequentists mostly do is they develop techniques of analysis that allows you to rule out stupid methods and to rank the reasonable methods. So it tends to focus more on analysis than on methods. But I did want to mention one general frequentist method. It's the bootstrap. It's kind of as automatic as Bayesian procedures. It can be used on all kinds of problems. It's just a general methodology that's very frequentist. So the bootstrap is that you take your original data set and you resample it multiple times. And in doing so, you're looking at alternative data sets. You're exactly being a frequentist from a methodological point of view now, not so much an analysis point of view. Of course, then there's analysis to show you that procedure has good frequentist properties itself. But it's very interesting broad class of techniques. Okay, so I think it's one more slide on kind of introduction, and I'm going to move on to some more concrete stuff. So what do you do as a frequentist? What kind of activities do you do? Well, you also write down models, you develop procedures and all that, but more, the kind of the analysis side of the story is there's kind of a hierarchy of mathematical things you do. First of all, you maybe try to prove consistency, that if there is a correct answer, you'll converge to that, no matter what that correct answer was. So that's often kind of fairly straightforward and not that informative. A more informative thing to do is to get rates of convergence towards rates of convergence. So two procedures are both good, they're both consistent, but maybe one of them has a faster convergence rate in terms of number of data points. Then I might want to prefer that procedure. A lot of work is done on that. And then more hard, but also very important, is to try to get sampling distributions that, as the number of data points gets large, perhaps I converge to some nice distribution, like a Cauchy or a normal or something like that, and then I can use that distribution to give me error bars. So I can get error bars by finding out the sampling distribution. Okay, so there is certainly work on consistency in the ML literature. There's some on rates, and there's very little on sampling distributions. So classical frequentist statistics focused on parametric statistics, in the 40s and 50s. But since then, it's mainly been non-parametric, really. There's a lot of non-parametric testing, and there's tons of other kind of non-parametric, function estimation, and all these large P, small n problems where these are going to infinity. The number of parameters is going to infinity as well as the number of data points, and so on. So often you'll see people say, well, classical statistics was parametric and so on, but that's just not. The tools were developed to be general. Non-parametrics is perfectly part of the story. One of the most general tools is empirical process theory. Empirical process theory talks about convergence of objects uniformly. So you find consistency rates of distribution uniformly on various spaces. Function spaces, parameter spaces, measure spaces, and so on and so forth. So statistical learning theory is really a part of that. It's a particular area of empirical process theory that focuses on 0-1 loss. But the tools there, Rademacher and all that, were developed in empirical process theory. And there's whole books on this. So if you're interested in theory, this tool is available. It's used to prove things about the bootstrap. It's used to prove things about M estimators, and so on and so forth. A lot of frequency analysis using this big, heavy tool. And then there are lots of other tools that are simpler, but that one's always available. Okay, I'm going to take a little pause to see if there are any questions, and then just kind of a stretching pause. And then the rest of my presentation today and the next time are going to be some little vignettes on research that I've been involved in that is all frequentist, and try to give you a better flavor of what frequentist activity really is like, what the kind of problems are, set them up, and see that there's some challenges there and see how to overcome them. These are going to be kind of machine learning methods, but then analyzed from a frequentist point of view and try to carry the analysis all the way through to the end. So I think I'll probably, in the rest of this talk today, talk about experimental design. And then the three things will be for the next presentation. So any questions on sort of the philosophical stuff first? Yeah?
Do you know any books that would cover both of these perspectives? I mean, a single book. Yeah,
I mean, one of my current favorite books is just kind of statistics in general is Ad van der Vaart's Asymptotic Statistics. Ad takes a Catholic view. He has got Bayesian and frequentist arguments throughout it. It's probably more frequentist overall, but it's got Bayesian theorems as well. Jim Berger, if you've not been introduced to James Berger yet, you should be. He's got a great book on statistical decision theory. The first edition of it was frequentist, and the second edition was Bayesian, and it's kind of good to read both of them. Anyway, in the second edition as well, there's a lot of merging of frequentist and Bayesian ideas, and I just think reading his book and his papers in general is a very good educational experience. Yeah.
Is objective base also subjective?
Is objective base also subjective? Well, yeah, sure, in the sense that I've written down a big complicated model, and some of the parameters I'm going to possibly be able to elicit subjectively. And there's a whole bunch of others that are often called nuisance parameters or whatever that I don't want to or can't elicit subjectively. I'll try to use objective Bayesian methods for those. So, most Bayesians do this actually in real life. They will sit down and say something about, well, this parameter I sort of believe is in this range for this or that reason. And there's this scale factor, I have no idea what it should be. Let's put a Jeffreys prior on that. Now, that's kind of an ad hoc thing to do, and there's a lot of ad hocery, but that's kind of you're in effect, blending objective base and subjective base. So I think of objective base as kind of a big tent that incorporates subjective as well as objective ideas. Yeah?
You said reference priors maximize the distance between the prior and the source.
Yes.
That means your priors are functions of the data.
Okay, no, the priors are not functions of the data in reference priors. This is as you're sitting there, you haven't seen any data yet at all, and you're thinking about what prior should I use? Okay? You're free to envision data sets you could get. You haven't seen any data yet, but you're free to sit and imagine possible data sets you could get. Okay? And the divergence function in the reference prior is an expectation over possible data sets you could get. So in fact, it has a little frequentist kind of mathematical character, but it's perfectly Bayesian. Bayesians are free to dream about data sets, and not just one data set. Yeah.
To follow up on that, I mean, if you have to imagine the possible data sets that you're going to get, are you then solving the problem you want to solve? I mean, don't you need, from a Bayesian perspective, your posterior in order to know which data sets?
How do you get your posterior? You need your prior to get your posterior. Where are you getting your prior from?
Yeah, no, but I'm just saying, like, if you say, I need to use, imagine the data sets that I'm going to see, but isn't that the whole point that, isn't that knowing your posterior? So if you don't know your posterior, how can you do that?
No, I wrote down a probability model in the beginning. Everybody agrees you sort of have to start there. Okay? And now I can imagine data sets under that probability model. So that defines my probability measure, and I can go from there and now take averages with respect to that. And that's what the reference priors does. You just need the likelihood. And given the likelihood, you do this divergence maximization thing. That gives you out a prior. And now you see a real data set. You put your prior together with your likelihood on that data set you observed and do a posterior. It's perfectly Bayesian. Yeah.
So just to follow up on that, the reference prior does depend on the size of the data set that you're expecting to
Yeah,
it
depends on that. It sort of has an experimental design flavor, and which is arguably a good thing. You kind of want to think about how your data will be gathered. And there's a Jose Bernardo was the first person to talk about this in great detail, and he's got a lot of papers talking about why experimental design should be taken into account in Bayesian arguments. A lot of the likelihood principle says you shouldn't, and that is sort of a misleading argument. Okay, so if you want to read more about this, read some of Jose's papers. Yeah.
So it seems that the subjective way you imagine your potential data set you could have, trying to keep a prior that's kind of similar to that. So you imagine your data sets you might have and try and model that in the prior. And then in the objective framework, you try and imagine data sets you have.
No, your data sets you're measuring are on X space. So the data is in X. Now we're trying to use that somehow to get something on theta. Okay, so that didn't help you in imagining data sets in X to get something on theta. Right? Whatever you're simply trying to find a prior that under these data sets you're imagining, quote unquote, has as little impact on your posterior as possible. And it's pretty neat that you actually just write that down. You write down the Kale divergence with respect to prior and posterior. You average that over X. That's where the averaging is coming in. You don't know the X yet, so you can average over all these possible data sets. You average over X, you get the mutual information. And you solve that problem, and out pops a prior. And it often is a Jeffreys prior. And it has a lot of nice properties. I should go over to that side. There's a lot of questions here. Yeah?
So you said that frequentists use their analysis to rank different estimators.
Yeah.
But often, the only thing you can come up with are bounds on the quantity that are just.
No, not the only thing you can come up with are bounds. That's not true. A lot of statistical learning people only use bounds because somehow I think it's more the CS perspective. It has to be a bound. But most statisticians use asymptotics of all kinds, expansions that aren't bounds, but are hopefully tight.
Okay, but then is it necessary that optimizing those is going to give you the best procedure?
No, I mean analysis is kind of always grains of salt. You did an analysis and you got an answer, and there's a little bit of error. There's a Taylor third order term you neglected, and so on. But that's what mathematics is about, sort of getting an understanding and maybe not being quite exactly right, but hopefully get a guide and then explore it further. Yeah, there's no, I always rank that procedure over that. There's always a little bit of art to this kind of, and understanding the setting and the consequences. Yeah.
Are there any of the frequentist analysis tools available for evaluating methods that give out probabilistic predictions and soft predictions instead of point estimates?
That's what frequentists mainly are focused on is coverage, not not just the point estimates.
Sounds like predictive distribution, not confidence interval.
Yeah, your loss function can, for example, be a log loss on a predictive distribution. You can study that its frequentist convergence, in terms of some procedure. It's commonly done. Yeah, absolutely. Maybe one more question, then I do have a second part of the talk that I want to get to. So, yeah.
I use bootstrapping sometimes, but I worry about it being recommended as a super general tool because if you bootstrap your data set, then you often get 2 data points in exactly the same place. And now suddenly my model is going to go, ooh, low noise level, and do something crazy. So if I put it in a flexible Bayesian model, it's a bad idea.
Yeah, so there's all kinds of bootstrap literature, and there's the simplest bootstrap has some issues that occasionally can come up, but there's a general technique called resampling methods, and there's a lot of worry about that. In fact, you can prove there are situations where the bootstrap is not consistent. Okay, but there are better bootstraps which are consistent. All right, and there's just a whole literature. There's a book on resampling. Joe Romano and others have written a very nice book on that whole technology. So all right, let's take a short, I guess it's a 2-minute break, and let me have time to then get through the rest of my talk. Okay, those are all great questions, and I was glad to trigger all of them. I really wouldn't mind spending the rest of the time just talking about those things, but I do have some more material I want to cover. So I'm around the rest of the day. If people want to chat more about those things, I'm happy to talk to anyone about those. So as I said, what I'm going to do in the rest of my presentation today and tomorrow is go through some vignettes of particular problems and show you, get a little flavor of how you do frequentist analysis. Okay, so this first vignette is about loss functions in classification and about experimental design. So the main paper this was based on came out last year. My colleagues Joan Langen and Martin Wainwright. And there are two backup papers that also play some role in the development of these ideas. So this has to do with things like boosting the support vector machine and sort of classification algorithms. And there's they all kind of came out separately, and then there was some realization there's a lot of unity in the ideas, and there was frequentist analysis that came out. For example, it showed that they were consistent. So boosting eventually was shown to be consistent. It was not clear in the beginning, and support vector machine and so on. So we're going to try to face a harder class of problems. We're going to do not just classification, but also experimental design simultaneously with classification. And now we're going to ask, are things like the boosting loss, the SVM loss, and so on and so forth, still consistent even though you're doing this harder problem? And that I wouldn't know how to answer that question unless I did this analysis. And having done the analysis, then you actually learn that actually it turns out some classes of these loss functions lead to consistency and some of them don't. So it's kind of a little bit of surprise, and I'll leave you to kind of guess which of them do and which of them don't once you understand what the setup of the problem is. So the way we got originally involved in this was a practical problem that some people at the Intel lab in Berkeley had one of these early sensor networks, and they asked us to solve a classification problem here, which is that they had a bunch of sensors on a grid. This were up on the ceiling, and there was a little robot moving around, and it had a light source on it. And they wanted to know whether the robot had gone into a particular region of the room or not. So the region was some green region. It could be convex or not. They just wanted to know whether it had or not. These are highly noisy sensors, and so it was a kind of a hard classification problem to solve. But moreover, the more interesting part was that these sensors, there's one of them shown over there, have these little batteries, and if they transmit data all the time, the batteries run out immediately. So they need to transmit only a little bit of data, like 1 or 2 bits per time slice. So you can't transmit the real valued voltage you're sensing of the light. You need to transmit a quantized version of that. And the question then became, how do you quantize? What's the optimal way to quantize, given that my problem is one of classification? If it was just data compression, I know how to quantize. But now I'm trying to quantize for the purposes of classification. How do I do that? All right, so here's the abstraction of the problem. There's a bunch of observables x1 through xs that are often real valued quantities, but since they've actually gone through a analog to digital processor, they've actually become quantized, but the cardinality of the quantization is really big, so m is really, really large. All right. We're going to quantize those with quantizers Q1 through Qs, and these are distributed. So this is their different spatial locations, right? And so this Q here doesn't get to see any of the other x's. This is a local calculation. So this quantizer then spits out a Z1, which is the quantized version of X1, and so on. And this one, it really is quantized, and its cardinality is much, much smaller than M. And then the central, these then are transmitted to a central site over the radio, and the central site fits a discriminant function to the Z values and tries to predict, yes or no, you're in the green region. And of course, you were in the green region or you were not, and depending on the value of that hypothesis, you get different distributions on your light sort sensors. So that problem is called decentralized detection. It actually existed in the literature before we got involved with it. In the 80s, it was a hot topic in electrical engineering, signal processing. Okay, so the general setup is going to be XY pairs. Let's assume they're IED for simplicity. The Y's are going to be 0, 1. We're going to have a quantizer now that takes the original covariate vector X and turns that into a quantized version Z. is there's going to be a quantization space in which Q lies in, and Q is this space is some set of random mapping. So for our analysis, it needs to be a set of random mappings, but in practice, we would often implement it as a deterministic mapping. Okay? So Q is a random mapping. All right, now we're going to do a statistical analysis of this kind of object, and what kind of object is this? Well, this is known as an experimental design. And you often think of an experimental design as something like an analysis of variance table. A person comes in and they went to cell 1, 3, or cell 4, 5. That's experimental design. All right, but it's really the broad mathematical problem is really just a kind of a mapping from some space z to some x to z, and the mapping can be random. In fact, in the analysis of variance, it is. You come in, it's a randomized experiment. You're assigned to some cell under some random assignment. So the z space here would be the cell of the analysis of variance table, and that's a discrete variable. Right? And x comes in, it's the description of the person who gets put in one of these cells. So that's just one example of a mapping Q, but then there are many, many others. So to set it in generality, you just allow Q to be in some space, and then you have the space be characterized in various different kinds of ways. So I will use the language of experimental design. Quantization is a special case of that. Analysis of variance as a special case, and so on. If you prefer one of those special cases, think in those terms. Now, that's half of the problem is the experimental design, but the other half of the problem is the discriminant function, i.e. the classifier. So we have this family of classifiers that lie in some family, big gamma, and it's probably going to be a large family, non-parametric family. And our problem is to define the decision, like in our decision-theoretic framework, I have to know the decision. The decision now is two parts. It's to choose the quantizer, Q, and to choose the discriminant function. The output is this tuple. All right, and what's our loss function? Well, the risk is going to be the probability you made an error. So the quantized discriminant function value was not equal to the correct label. That is a 1-0 loss function. If I take the expectation, well, then I get the probability that they're not equal. So this is the risk function as a function of Q and gamma. So it's different notation, but it fits in my decision-theoretic framework we talked about earlier. Okay, so there are many applications of this. Okay, so if you look at the existing literature, there's sort of help on two sides of the equation, but not on both of them simultaneously. So the classical signal processing literature defined this problem of decentralized detection, and it assumed that everything is known except for the quantizer. Okay? Everything means that all the probability distributions are known, the class conditional probability distributions, the class prior probabilities, and so on. So all that's not known is Q. All right? And so how do you find Q? All right, and so let me make a little drawing. I didn't do it on the slides here. I guess I turn on the light over here. Light didn't come on. Did I do that wrong? No, light didn't work. So in my original space, there's the X space over here. That had class 1 and class 0, maybe looking like that. And it's sort of hard to fit a discriminant boundary among these two things. So I might want to use a mapping Q, which goes over to a space Z, which pushes them as far apart as possible. All right, that would be a good choice of Q. And if I did a bad choice of Q, it would smush them together even further. All right, so all I got to do is measure in some ways the divergence among probability distributions, and then optimize Q with respect to that divergence. What divergence should you use? All right, well, you're trying to maximize divergence here. Often we talk about minimum divergence. This is a maximum divergence problem. And so these guys said, well, what are some divergences you can maximize? And so they wrote down lots of kind of functionals on probability distributions, and they found that some of them were easy to maximize and some of them were not. And so they picked those, and that's what they did. All right, so Hellinger, Bhattacharya, a whole bunch of others kind of came out of that literature and became then famous in other fields. And they were set up because of this problem of divergence maximization. So lots of radar has been done this way. It's a big literature where people have just picked a divergence, say Hellinger, Chernoff, or something, and then it's a function of a probability distribution, but you assume those probability distributions are known. And so just write down the expected divergence, maximize respect to Q, and then pop out that Q back to the user. And so then you put that into your radar, and the radar quantizes in that way. It's called signal set selection. All right, so that's the story, and I would view this as basically a heuristic literature. You can turn the lights off now, or do I have control? Okay, I have control. So it's heuristic. What did I do?
Yeah, there are two sets of switches. So.
All right, so it's basically using a plug-in and then not really worrying about how well it performs. You put it in, and you don't then try to evaluate how well that does. All right, so the statistical machine learning literature, on the other hand, has focused on problems where the whole problem is to find the discriminant function and not worry at all about the experimental design. So you assume that that's known, and you try to find that. Okay? And the way it's done is by defining a surrogate loss function. Boosting, logistic regression, support vector machines are all based on surrogate loss functions. And this is, it's more rigorous. There's a decision theoretic flavor. There's consistent results, and so on and so forth. But it's really facing the whole problem, which is to find the Q and the gamma simultaneously. Okay, so let's build up a little more machinery. Let's talk about these f-divergences. These are the guys that have been discussed by the signal processing literature. And of course, they then appear in many other literatures as well. And kind of part of this talk is going to be to somehow unify these things. It's not just a list of things in your mind. There's going to be relationships here. Let's talk about discrete random variables just for simplicity. So I'll write sums instead of integrals, but you can do this with continuous as well. So you define the f-divergence between two measures, mu and pi, as f of the likelihood ratio, and the integrate, or you average with respect to the pi. Okay, so that looks kind of like KL divergence, and in fact, if f is chosen to be u log u, you get KL divergence. All right, but if f is chosen to be absolute value of u minus 1, for example, then you get out the variational distance, which is here, just the L1 distance on measures. F can be any continuous convex function, so these are particular examples, but here's another one. And if you plug that one in, you get out the Hellinger distance. And this goes on for several pages. So you plug in any continuous convex F, and you look at, you now define the new Ali-Silvi or f-divergence. All right, so why did these guys use the f-divergences? Well, they were somehow intuitively appealing, but there was a little bit of kind of underlying theory behind that choice. It's not entirely satisfactory. In fact, it's not really satisfactory at all, but it's a good starting place. And the theorem was due to David Blackwell in 1951, a classical paper, well worth reading. Had a big impact on economics. And so his theorem stated the following. If a procedure A, i.e. some kind of an estimator, has a smaller f-divergence than a procedure B for some particular choice of f in your f-divergence, okay, then there exists some set of prior probabilities. These are the class probabilities. You're in one class or the other. So some set of prior probabilities on the classes such that procedure A has a smaller probability of error than procedure B. Well, that's what you care about. That's the risk. So we've now just learned that procedure A has a smaller risk than procedure B. That's good. We should now choose procedure A. And we were told that by looking at f-divergences. So somehow f-divergence gives us some information about risk. Right? Well, this is just an existence statement, though. It says there exists some set of prior probabilities. We don't know what the prior probabilities are for which that f-divergence gives us this ranking. And we don't know in our particular problem which f-divergence to use. Okay? So it's not that helpful. It's not at all helpful in practice. But it does at least suggest that f-divergences are not unreasonable objects to be looking at if you're trying to minimize the probability of error. And that's a good thing because minimizing the probability of error is, of course, a non-convex problem. The risk, the 0-1 loss is non-convex. And so you try to find some other kind of function you can optimize, and these things are convex, and therefore you might try them by this theorem. So that's what people did. There's famous papers, Kyleth in 1967 and so on, choosing particular divergences and just kind of, in some sense, hoping that the priors now were right for that f-divergence on that particular problem. Okay. All right, now there are some supporting arguments for asymptotics. You know, these divergences also arise in other ways. In fact, the original Kullback-Leibler divergence arose by an analysis of hypothesis testing. It characterizes the power function in hypothesis testing where your two classes are staying at a fixed distance apart as the number of data points gets large. And similarly, Chernoff distance arises when you do that same analysis in the Bayesian setting where you have priors on your classes. So these divergences were, you know, kind of in some ways talking about probability of error directly in this case, but you know, it's an asymptotic argument and it's hypothesis testing. So anyway, it's still a heuristic literature. All right, now let's turn to the other side of the coin, how to choose the discriminant function. And so you kind of now know this stuff. This is machine learning kind of 101. You choose a loss function that measures the distance between your class label and your discriminant. We're going to start with the 0-1 loss. It's kind of the real loss we're trying to optimize. And in the binary case, you can write that as the indicator function of when the labels disagree. Okay, if the labels disagree. In fact, now I'm using y is 1 minus 1, and the discriminant function outputs also a 1 or minus 1, or a real number in general. So if they disagree in their sign, that's bad, and you pay a loss of 1 in that case. Otherwise, you pay a loss of 0. Okay, so main focus is on the discriminant function. Now we know also, from this point of view, it's intractable to minimize 0, 1 loss with respect to this argument as well. So instead, what people have done is they've picked these surrogate loss functions, which are convex upper bounds on the 0, 1 loss. So hopefully you've all seen this picture. Here is the 0, 1 loss expressed in terms of this margin value, i.e. the product of the y and the gamma of z. And if you disagree, you're on this side, you pay a loss of 1, otherwise you pay a loss of 0. And so it's intractable to optimize this. Instead, people look at these upper bounds. And the blue line is the support vector machine, the hinge loss. The red one here is logistic. The green one, I think, is the boosting loss, the exponential loss, which is what gives you boosting. And there's a whole bunch of others that this page could be littered with examples. Okay, so all those different procedures aren't that different from a optimization point of view. You just write down these, you just optimize over these particular choices of curves, and then you hopefully try to prove something about them. What can you prove about them? Well, let's try to set up a little bit of the theory. We're doing optimization here. This is sometimes, well, in statistics, this is called M estimation. M estimators, you write down a function. Often it's called a contrast instead of a loss to distinguish between the thing you're trying to analyze. This is a procedure, not an analysis. But you're optimizing, and that's called M estimation. In the machine learning literature, it's often called empirical risk minimization. It's the same idea. All right, so we have this ID training data. We write down an M estimation functional, which is this object here, which just takes our contrast function or our loss function, say the exponential loss or the hinge loss. We sum that up over our data sets, and we call that the functional we'd like to optimize. So it's an empirical risk, if you will. Okay? All right, so here's some theory for this object. This is a paper that my colleagues and I worked on that gives you necessary and sufficient conditions. There have been work on sufficient conditions. This gives a full treatment of these surrogate loss functions. It gives both necessary and sufficient conditions for consistency. So we're trying to say, if you use these loss functions, did you get the same answer at the end as if you had optimized the 0, 1 loss? That would be a satisfying story. And all those guys do that, and here's a theory that tells you that that is the case. All right, so first of all, not any arbitrary phi can be used. It has to satisfy some properties. In particular, we had a very weak condition called classification calibration, which is essentially a form of Fisher consistency. And here's an equation that defines it. Let me not spend a lot of time on this, but basically this says that if you disagree with the right answer, you pay a bigger loss. That's bigger than if you don't disagree with the right answer. Okay, so this sort of says that things kind of tilt up to the left. That on the left side where you're making an error, you have a bigger loss than on the right-hand side where you're not making an error. Okay? So it turns out to be necessary and sufficient for what's called Bayes consistency. It's not a Bayesian notion, as I hope you remember. I talked about Bayes risk earlier in the lecture. This is consistency in the sense of the 0, 1 loss. Okay, so we will now define a surrogate loss function to be something that is classification calibrated. That's the definition of this object here. It satisfies this property. All right, now you can forget this definition because in the convex case, where phi is convex function, then it's classification calibrated if and only if it's differentiable at 0 and it has a negative derivative at 0. So all those curves, and don't turn on the light because it's not worth it. All those curves tilted like this at the origin, they had a strictly negative derivative here, and that's all you need for classification calibration. So it just matters what happens around the origin. Okay, so that's just a kind of a setup for the rest of this talk. That's what we mean by a surrogate loss function. And it turns out that those surrogate loss functions defined in this kind of machine learning literature turned out to have a very nice relationship to f-divergences. Sort of surprising but true. So there's going to be a constructive and many-to-one correspondence between surrogate loss functions and f-divergences. They go back and forth in two directions. And having done that, there's going to be now two spaces we can work on. You can be interested in loss functions, and you can go instead and work in the space of divergences, or vice versa. And by doing that, we're able to define a notion of equivalence among loss functions. So two loss functions will be equivalent if they map roughly over into the same f-divergence. Not quite, that's not exactly right. There's kind of a range of f-divergences. But we will define a notion of equivalence. And with that notion of equivalence in hand, it's going to be extremely easy to prove things like that this procedure is consistent or this is not, and so on. It's kind of a nice characterization of a space of loss functions. So space of loss functions has some structure. It's not just a list of loss functions. It has a lot of structure to it. And we have a theory that shows, that explicates that structure. Okay, so I got about 10 minutes, right? Is that actually correct? Is that?
Yeah,
Give or take 5. I started a little late, but I'm trying to figure out where to. I'm going to be in the middle of this talk by the end of this, so I'm going to figure out how far to go. Okay, so let's just set up a little bit of notation. This is kind of dull, but necessary notation. So remember, the risk function is a function of it's the expectations, the frequentist expectation of the loss, and then the data is the y and the z. It's a tuple. And then the parameter, which was theta back in the original slides, has now become a tuple as well. It's both the discriminant and the quantizer. For simplicity, it's going to be nice to work instead with conditional distributions of z given y, the unnormalized conditionals, i.e. the joints. So mu of z and pi of z are these class conditional densities unnormalized. So little p and q are the priors. Q is 1 minus p. And then we integrate out the x, which is the unobserved covariate. And so this is now just a function of z. Okay? So we take the class conditional distribution, integrate that out under the quantizer, and we get a distribution on z. Okay, and so using this notation, you can now represent the phi risk. The expectation here is, of course, over the two values that y can take on. And so if we just do that expectation over the y, we get a mu and a pi, and we get a minus from y equal to minus 1, and a 1 where y is equal to 1. Add those two up, that's the expectation over y, and then we do the expectation over z, where the mu and the z are the measures. Okay, so that's just a representation of phi risk. So this kind of has a little bit of a convex flavor. The phi tilts in one direction, and phi of minus tilts in the other direction, and this is a convex combination of that, kind of roughly speaking. It has some convexity properties already emerging. Okay, so now, as a frequentist, you're free to do something what is called profiling. I have a function of 2 arguments. And how do I get rid of one of the arguments so I can optimize with respect to the other argument? All right, well, if you're a Bayesian, the only thing you know how to do is to integrate out one of the arguments. But how do you integrate out the discriminant function? I don't know how to do that. But I can optimize it out. That's called profiling in statistics. To optimize out one argument so you can focus on the other argument is called profiling. You often have the profile likelihood, for example. All right, so let's profile this risk function by optimizing out the discriminant function, and we get a function now just of q. And then we could use that as a function for choosing q. Okay, so let's do that now for some examples. So if we choose 0, 1 loss, you can easily figure out, you can do this optimization. And the answer is just that it's a sign of the difference of the two measures, which makes sense. If you're doing 0, 1 loss, you want to pick the guy that had the bigger measure. So you plug that back in to this optimized, you will get this function here. And I've just done that in a couple of steps here. If I plug it in, you just have to do a little calculation. If you're used to work with classification, you will know how to do these calculations. If not, get out a sheet of paper afterwards. It's really easy. You plug back into the 0, 1 loss, you get this minimum. Right, makes intuitive sense. You should pay the loss of the worst of the smaller class. And if you just then, the absolute value is equal to this minimum, which is really easy to see. And then this thing here is 1 minus the variational distance, just by definition. Okay? All right, so it turns out this profiled risk happened to be the negative of a divergence. That's kind of interesting. So if you use this divergence, effectively what you were doing was working with the profiled 0, 1 loss. That's kind of interesting, all right? Okay, so we did that calculation, and we thought, well, does that hold more generally for other kind of losses other than 0, 1 loss? And it turned out it did. It turned out it's a really fun exercise to do this for all kinds of losses. If you start with the hinge loss, for example, and you profile out the discriminant function, you will get 1 minus the variational distance. So it turned out that 2 different losses mapped into the same f-divergence. Kind of interesting. So it's not. We thought it might be 1-to-1. This immediately proved that it's not 1-to-1 relationship. What about if you start with the exponential loss, the boosting loss? Well, it turned out then you got the Hellinger distance, and that's a nice little exercise for you to do. It's kind of surprising that the exponential function goes into a square root. If you start with the logistic loss, you got out something looking like this is the KL divergence symmetrized. It's called the capacitory discrimination. And so on and so forth. So all the losses we could write down, they all turned into f-divergences. And so we wondered, is there a general theory behind this? All right, it turns out there is, yeah.
Yeah, so why do you not consider the square loss?
Let's talk about that. I'm about to finish, and I want to that would take me a little bit of diversion, so let me tell you about that a little bit later. So it turns out that there is a general relationship here that this class of surrogate loss functions maps over into the class of f-divergences. For every surrogate loss function, there is a corresponding f-divergence, and for every f-divergence, there is a class of loss functions. And these partition the space and exhaust the space of surrogate loss functions. So it's a complete characterization of the space of loss functions in terms of f-divergences. Okay, and so I'm going to give you a little flavor of how that's proved. It's a theorem in that an Annals paper I mentioned. The key tool underlying it is my favorite tool of convex analysis called Conjugate Duality. Unifies lots and lots of things. So just to remind you what Conjugate Duality is, it is if you take a lower semi-continuous convex function f, the convex dual is defined as the supremum of a linear functional minus the original function. That's necessarily a convex function. Okay? So the star means conjugate dual. So we're going to work with f star of negative beta for technical reasons. So this psi of beta is the thing to remember. It's the conjugate dual function up to this flipping of the sign. Okay, I think on the next slide I have the theorem. Yeah, so let me just take a minute to explain the theorem. So this is the theorem that shows that we have this, this relationship between divergence and losses. So one direction is pretty straightforward. For any margin-based surrogate loss function, there is an f-divergence such that when you profile out the loss function, the discriminant function, you get the negative of an f-divergence for some convex function f. So that goes in one direction. Moreover, in going in that direction, it turns out that for phi that is continuous, that you get some nice properties of that conjugate dual function. These are sort of technical. It's decreasing and convex. It has a fixed point property, and there's kind of a cascade property, kind of fixed point-like property here. So let's not worry about the technical details. It's just that it turns out even if you have this weak condition on phi that's continuous, which all the ones in practice are, that you get out these kind of mathematical convexity type properties of the conjugate dual. Now, the other direction is really the interesting one, which is that if f is a lower semi-continuous convex function that satisfies these conditions when you take its conjugate dual, okay, then there exists a loss function that induces that f-divergence. So this goes in the backwards direction and shows that f-divergences also characterize loss functions. Okay, the forward direction is actually trivial to prove. It's one page. And the backwards direction requires a lot of convex analysis and is definitely non-trivial. So here's the easy direction. Even though it's in the lecture, I can take you through it. It's pretty easy. Here's the risk function. Remember, I wrote that down a little while ago. Now let's profile that. Let's optimize out the discriminant function. All right. Well, when you optimize this out over gamma, we're going to do this for each z, and so we can move it inside and replace gamma of z with just a number. So we get this expression inside. Okay. And now let's just pull out pi of z, and now we are left with this expression here. Okay, just dividing by pi of z and pulling it out. All right, and now if we look at this object right here, this is a function of the likelihood ratio, and moreover, this is a convex function. All right, because here it is. I just wrote it down here. It's just there's a bunch of linear. If it's a family of linear function, you take the infimum, that gives you a concave function. You flip the sign, you get a convex function. So we've identified the f. It's just this function, and this thing is now pi of f of the likelihood ratio. It is an f-divergence. So all those little examples we were doing were all just examples of that. So that's really very, very easy. Okay, the other direction is hard, but there is a constructive consequence of it, which is that when you go through that proof, at some point you identify the loss function. You can write it down. It has a certain form. For alpha, which is equal to 0, it's just this fixed point. For alpha bigger than 0, it is the conjugate dual function of a free function g. This is like a degree of freedom. You can choose any g you want that is increasing, continuous, and convex. I'll give us some examples here on the next slide. So psi of that function, and then when alpha is negative, you just get the g function itself. So it turned out that psi had this form as part of the proof. So this kind of gives a little structure of the possible loss functions you can get, and also points out to where the freedom is. It's this g function. Now, so you can now do this for some examples. So if you start with the Hellinger distance, remember that is the f-divergence where f is equal to this square root function. All right. If you now just take the conjugate dual of that, that's a little easy, actually just a piece of calculus to do that. You'll get this function. That's the conjugate dual of the square root function. And take the minus of that, and now that's the psi function. I've calculated it. And now I can choose a bunch of g's and plug them into psi and I get out loss functions. And so if I use g equal to e to the u minus 1, that's a particular choice of g, then I get out the red curve, which is the exponential loss. So we've gone in the opposite direction. We start with Hellinger distance, and we recovered the boosting loss. But also I could choose other g's. If I chose g equal to u squared or g equal to u, those are continuous convex. Then I get these other loss functions, the green and gray curve, which are equivalent to the boosting loss in that they map into the same divergence function. Okay? Yes?
So you started with an f-divergence, and then this gives you constructive proof to go backwards and find.
Correct.
Find the entire class of loss functions?
Okay, it defines the entire class. It exactly does. It's a characterization. It just turns out it's not as strong as we need for a statistical theory. The statistical theory actually defines even a little broader class. You take a f-divergence and you broaden it out a little bit, and you go backwards to get all losses that map into that. And those things turn out to be universally equivalent. So you're already heading in the right direction. But it turns out that for the reasons I'll get into, it's a little broader than just one f-divergence. It defines the kind of the whole statistical story. Here's the variational distance. If you'd liked the hinge loss, you would have started with the red curve there. The underlying f-divergence is based on the variational, and as we saw on an earlier slide, you can write that as the using f is equal to the min. If you take the conjugate dual of that, you get out this function here. It's kind of got the hinge kind of look to it. And if you plug in then different choices of g, you get out these different curves, including the hinge loss, and some other curves which are equivalent to the hinge loss in terms of giving you the same variational distance as the f-divergence. And Kullback-Leibler, you can kind of play the same story, and so on. So I am about ready to run out of time. Let me see. Let me just page through a couple of things so I can see where I am, because I'm going to stop here. Okay, I think I'm going to just, let's see, Bayes consistency, and then the universal equivalence story, and then the theorem. So there's 3 theorems here. I'm not going to get to theorem 3, which is the favorite one, but I'm going to do just, let's see, where was I? Yeah, I think I'm just going to set it up, and I'm going to stop there. So. All right, so I've given you a theorem that relates f-divergences and losses, and now I'm going to kind of anticipate what use we're going to make of this theorem. So the 0-1 loss is the goal of classification, so let's start with that. And we now map into divergence space, and we get the variational distance with f chosen this way. Okay? Now, that's plug it in right here. Let's now consider a broader class of f-divergences defined by taking this kind of affine expansion of the original f-divergence to the min of u1. This is kind of a bigger class of f-divergences. All right, and now let's get all those f-divergences. So if I could draw a little picture here, and this will return next time. So we've started with a particular loss we care about, the 0-1 loss here. We mapped over the space of f-divergences there, and we got the variational distance. And then we're going to now broaden out a little bit and get a class of kind of all the affine combinations sort of thing of that one. And then we're going to go backwards and get a broader class of loss functions, all the ones that map into here. It's kind of composed of several subsets. There's a whole bunch of them over here. All right? And it'll turn out that all of these over here have the same statistical properties as the 0-1 loss. All right? So you get consistency immediately for all of them. All right? And anything outside of that does not. They're not universally equivalent. So we can prove lack of consistency and consistency. All right, so you don't see that yet because you don't know why I picked this particular affine thing, but you'll see that in theorem 2 or in theorem 3. But anyway, let's just assume that that's a reasonable thing to do. We do that, and immediately that's going to tell us about Bayes consistency, and will also give us the converse, which that only these phi losses yield Bayes consistency. Okay, so I've set up this story. I guess the slides will be available. You can look ahead if you want to read the annals paper. If you have nothing else to do with your time, you can see these theorems and see how they're proved. All right, let me stop and see if there are questions on this half of a story. Yeah.
Why do you not consider square?
Okay, so all right, so this talk is about classification. Okay, so we are centered around 0-1 loss, and we're developing a kind of a theory for that. Okay, there's a whole other sort of story to talk about, other loss, so kind of the focus of the loss. So if I was doing regression, I would develop a different parallel story here. When I get to the end of this sequence of theorems, I will be able to say a little bit more about that. All right, but let's just focus on binary classification for now.
Yes?
Instead of mapping to divergences
would it also make sense to look in the space of kernels? Because early in the summer school, one of the lecturers was saying that there's more widely use of kernel methods in order to quantify distances between distributions.
Yeah, no, so we worked on distance between distribution defined by kernels. And in fact, one of the applications of this will be to that at the end of this talk. So we'll talk about kernel space characterizations. And essentially it comes about by having a function space over which you optimize. And that function space can be a kernel space. It's just one particular choice. All right, so it's just one way to get a kind of a rich class to optimize over. So it's not a fundamental part of the story, but it's just kind of a convenient part of the story. Yeah?
When you define this universal equivalence, are all the estimators within that equivalent even for the purpose of statistical efficiency? Or?
Okay, let me tell you in one sentence what it is, and you'll see it next time. A universal equivalence means that if two procedures are ranked the same by the f-divergence, then they're ranked the same by the loss. So it's kind of the Blackwell theorem that I mentioned earlier, but extended to the whole class of divergences and loss functions.
But for any given data set?
For any given probability distribution. It's universal in the sense of any probability distribution. That's right. So we'll be able to say if you're not universally equivalent to the 0-1 loss, there must exist some probability distribution where you'll get a different answer than the 0-1 loss would give you. Right? And so in that sense, it's not a satisfactory loss function to be using because you can get it wrong. Sorry?
It's only asymptotic.
No, this is not an asymptotic theory.
Okay.
Let me see if someone else has a question, then I'll come back to you. Okay, go ahead.
I'm not very familiar with f-divergences, but in general, can you give us a sense, what is so special about the mathematical properties of f-divergence such that it works for f-divergences but not other types of...
Convexity.
Oh, okay.
That f function, it's a convex function of the log likelihood ratio. That's the key. Yeah.
So within this kind of equivalence class of losses that statistically are similar to 0-1, is there a best one? Is there one that most closely?
Great question. No, this theory is silent on that. It just identifies the class. And then I return it to you and I say, now you choose among that class according to other principles, say computational complexity in particular, or sparseness, or some other principle that goes beyond decision theory. But I think that's a good thing to do. So I'm going to narrow down my class and say all these are good, and now you can bring another principle to bear on choosing them among them. So I don't want to tell you at the end of the day you have to use that one. That's kind of not the frequentist spirit. It's rather to say that if you want to now carve it down further, you better bring another principle to bear. Computational complexity, sparsity, some other principle. Yeah?
It looks like in the derivation, there was a non-parametric assumption in the sense that you could optimize for each, when you do your profiling to optimize over discriminant function, you could do it independently for each Z.
No, that's not an assumption. But you're right, it's non-parametric in the sense that it's over all possible gamma.
But
that step wouldn't be true if it was restricted. It's over all measurable functions gamma. Which is
if I have a rich class.
That's right. So our eventual theorem of consistency is going to have to be in a sieve of some kind, where we're actually going up to a rich non-parametric class. But that's the spirit of this kind of whole story, is to do this for, things like support vector machines, which are supposed to converge for all possible generating distributions. All right. Since the popcorn has stopped popping now, and we're done.